we would like to calculate the electric field due to a symmetric distribution. The distribution we're going to look at is an infinite thin plane with a uniform charge density sigma. So we have an infinite thin sheet. And we want to find the electric field on both sides of the sheet. Now, the first argument is by symmetry, that if we picked a little piece up here, dq, and if we picked another piece down here, call this dq1 and dq2, and we looked at a point P over here, this piece is producing an E field dE1, and this piece is producing an E field dE2. And so when we add these together, these two pairs of charges produce a field that points away from the sheet. Now, we can take the entire planar sheet and divide it up in pairs and have a similar calculation, which tells us that on either side of the sheet, we expect the electric field to point away from this positive sheet. And this is because the sheet is infinite. We also expect that if we took some line that's parallel to the sheet, that the electric field magnitude along these lines would be uniform. And that will help us decide how to choose our Gaussian surface. So this is what we expect from the symmetry of an infinite sheet. Now, in this problem, we have two regions, on the left and on the right. And let's put our sheet at x equals 0, and we'll call this our x-axis, and we have a unit vector I hat. And this is the beginning of the setup for this problem. And now we can apply Gauss's law by choosing a Gaussian surface. So let's draw our sheet again, plus sigma. And by the symmetry of the problem, the best Gaussian surface that we can choose is a cylinder, a little Gaussian cylinder. And we want both of these sides to be the same distance. And that way, the electric field on both sides will be the same in magnitude by the symmetry. Remember that the unit normal on this end cap points out, and the unit normal on that end cap also points out. And our Gaussian surface has three different faces, two end caps and a body in which the unit normal points out on the body. But because the electric field is tangent to that, there'll be no flux through the body of the surface. And so now we can apply Gauss's law, where we're calculating the flux dA. This is through our GS. We'll call GS the Gaussian surface. Makes it a little bit easier. And over here, we have the charge enclosed in the Gaussian surface divided by epsilon naught. Now, it's always a good idea to illustrate where that charge enclosed is. It's where the sheet intersects the Gaussian surface. And now flux, E is pointing outward. E is pointing outward. It's the same magnitudes. If we make this area of the cylinder A, then we have EA on the left plus EA on the right, and through the body, 0. Now, the charge enclosed is just our sigma times the same cross-sectional area, and we're dividing by epsilon naught. And Gauss's law equates these two different physical quantities. And so we get 2EA equals sigma epsilon naught A. And so what we have in Gauss's law is the magnitude of the electric field. Now, because this quantity was positive, it agreed with the way we chose our arrows. But notice that the direction of the E field is in opposite directions. And in our regions 1 and 2, this side x was negative, this side x was positive. We now want to express the fact that an electric field think of it as an arrow in space at every point in space. And we need different descriptions for the arrows on the left side compared to the right side. And here's how we would write our answer now. We would say that the electric field for x positive is sigma over 2 epsilon naught I hat. That corresponds to pointing in the plus x direction. And on this side, same magnitude, but minus 2 epsilon naught I hat for x less than 0. And that's how we can express the vector fields for all of space. But notice that there's this discontinuity at x equals 0 because this is a very thin sheet. And in fact, if we made a graph of the x component of the electric field as a function of x, we see that that component is negative. There's a discontinuity here, and on this side, it's positive, and the value here is sigma over 2 epsilon naught, and the value down here is minus sigma over 2 epsilon naught. And so that's the electric field for a single thin sheet using Gauss's law. We would now like to calculate the electric field of two very thin sheets that are infinite. One is plus sigma, and the other is minus sigma. Now, we're going to look at this one two different ways. The first thing we want to do is think of this as a superposition problem. And after that, we'll show another approach to do it. So as a superposition problem, we would look at it like this. So I want to make it adjacent to it. First, I'll calculate the field of a positive plate. Now, we've done that calculation already. And what we know is that here there are three regions: outside, between the plates, and also outside. So we know that the electric field points away from a positive plate, and it's uniform. And I'll just imagine that the other one is here. And so I've drawn arrows in all three regions of space due to this infinite positive plate. Now we want to add to that a negative plate. So here we have minus sigma, and I'm just going to show the three regions of space also. And we know that the field for a negative plate points towards it, E minus, E minus, E minus. So I've drawn these fields superposition for the positive plate and the negative plate in the three regions of space. And when you add these two together, we'll do the addition over here. We have E minus plus, we actually used a different color, E plus. And in this region, we have E plus. Down here, we have E plus. Here, we have E minus. And here, we have E minus. So when you see when we add them, because the magnitudes are the same, it's sigma and minus sigma, that the sum here will be 0. The sum down here will be 0. And in this region here, the sum will produce a field that's going from the positive plate to the negative plate. So our vector sum will point down, and that will be the total field. Now, let's express that with a unit vector j hat, say up. So in region 2, we have that the electric field in region 2 is the sum of E plus E minus. And now we can write vector expressions for each of these things. Notice the E plus is in the negative j hat direction, minus sigma over 2 epsilon naught j hat. Where did I get this result from? That's the field of a single plate. And the field of the negative one is also downwards. Remember, it always approaches. E fields point towards the negative plate. And that one's downward too, with the same magnitude, minus sigma over 2 epsilon naught j hat. And so we see that the field between the plates is sigma over epsilon naught minus j hat, and it's 0 above, between, and 0 below. And that's the electric field for two parallelly opposite charge plates using the superposition principle. Now I want to show a different way that we can apply Gauss's law to get the field using the fact that this is what we know by symmetry the field should look like. So now let's draw the total distribution again, plus sigma, minus sigma. And we have in this region, which we called region 2, the electric field points down, and E in region 1 was 0, and E in region 3 is 0. And this is already the superposition of the field from both plates. Now I can use Gauss's law by choosing a Gaussian cylinder that looks something like this. It only cuts through the upper plate where our charge enclosed is right here. Now, even though we have an n hat in region 1 and an n hat in region 2, there's no electric field on region 1. So our Gaussian law calculation for flux, and now I'll denote flux by just our symbol phi of E, and over here, charge enclosed over epsilon naught. There is only non-zero flux through this bottom plate, remember the cross-sectional area A, and so we have the E field in region 2 times the area is equal to the charge enclosed, which is sigma, only sigma, times A over epsilon naught. And when we equate these two things by Gauss's law, we see that the electric field in region 2 has a magnitude sigma over epsilon naught. And again, if we want to express that as a vector, we can write that the vector E points downward minus j. And that was the same result that we had before. Now, this does require one point, because when people look at this calculation, they often ask the question, OK, we've calculated this field using Gauss's law. Now let's just add the field of the other plate. And the reason you can't do that is we've already included the information of this plate by saying E was 0 up there. That's where that information is contained. And when Gauss's law is just the charge enclosed in the Gaussian surface, and there's no part of this charge that's in the Gaussian surface. And that's the remarkable thing about Gauss's law. It's the flux through the Gaussian cylinder is equal to the charge enclosed divided by epsilon naught. And so that's an alternative approach to calculating the field between two equal and opposite charged plates.